Okay, let's talk about exponential functions. So an exponential function has this form. So now, what's different about this is x, your independent variable, is in the exponent. Before we had equations like x squared and x cubed. Now we have some constant value. We call this the base, raised to a variable. So this is an exponential equation. Here's some other examples of exponential equations. Maybe we have f of x equals 2 raised to the power of x, or say y equals 1/2. A is 1/2 raised to the power of x. Perhaps we have f of x and 1/2 is written as a decimal raised to the power of x. So we could see these exponential functions in a number of different forms. Now at this point you might want to jump back and review chapter 1.2 for exponential functions and operations. But having said that, let's go on. So if I have this function and I were to plot it, it would look something like this. Here's our Cartesian axis, x and y. So let's set this up on a table here where I have f and the value f of x. And let's start putting some values in here. So when x equals 0, f of x equals 1. And when x equals 1, f of x equals a raised to the power of 1 equals a. So that's going to always be the case. And then if we go bigger, if x equals 10, this is a to the 10th power. And as we continue on with this process and we approach infinity, this value is just going to approach, well, we'll see what it approaches here in a second. So let's plot some of these. So 0, when x is 0, y is 1. So 0, 1 is a point on this curve. Then when x is 1, y equals a, we're going to assume it's bigger than 1 here. Y equals a when x is 1. So that's this point, 1a. So those 2 points are always the case in all exponential functions of this form. And as you can see, as we get bigger and bigger and bigger with our x values, a grows, well, it grows exponentially. It grows really fast. So as x goes to infinity out here, as x gets bigger out to infinity in this direction, really? Come on. Then, in this direction, the function just gets bigger and bigger and bigger too, without limit. So it also goes to positive infinity. So here we are at 0. Let's do this in orange. We come up through here, and we have what we might call exponential growth. We grow exponentially. So this is heading towards y value of infinity. Okay, so what does it do on the other side of the y-axis? Let's continue to investigate this. So when x is, well, when x was 1, this equals a. When x is minus 1, this is a to the minus x, which is the same thing as a to the x raised to the minus 1 power, which is whenever you see a negative in your exponent, that flips down into the denominator, a to the x. So 1 over a to the x. And when a is minus 10, this will be 1 over a to the 10. And when a is minus 100, this will be 1 over a to the 100, and so on. So the denominator keeps getting bigger. If you go take a calculator and you put a bigger number in your denominator, 1 divided by the bigger number in your denominator, you're going to see that as this thing heads towards minus infinity, so as it's heading out this way, towards minus infinity out here, then your function starts to approach 0. Never touches it though, but it gets really, really close to 0. So this thing then gets really close to 0. And that's what it looked like. That's what it looks like. So we're only going to talk about situations where a is greater than 0 and a is not equal to 1. If a were to equal 1, then it wouldn't matter what x was, the function would always equal 1, so it would be constant. And if a was less than 0, the a term here, less than 0, we're not going to deal with that situation. So we're always going to only talk about these two situations. All right, so let's plot again an exponential function. This time we're going to give a value. We'll call it 2 to the x, raised 2 to the x power. Okay? So again, when x is 0, 2 to the 0 equals 1. So this crosses at exactly the same place that all of these exponential functions cross. It crosses at 0, 1. It crosses the y-axis. It's the y-intercept. And now when x is 1, this is 2 to the 1, or 2. I guess I just put a straight line here. So this point is up here. So this is 1 comma 2. And this thing is going to grow then exponentially like this. Now when x is minus 1, this is actually 2 to the minus x. So this point here, 1 over 2 raised to the 1 power, or so 2 raised to the minus x is the same, or 2 raised to the minus 1 is the same thing as 1/2. So this is minus 1, 1/2, and we can see we're getting smaller, and then as this goes on, it'll get even smaller and smaller and smaller. So again, that's how it looks, just like it looked before. Okay, so let's look at another function where we make a small change to this, and we look at f of x equals 2 raised to the minus x power. Well, again, this is 2 to the x raised to the minus 1. So that means this is 1 over 2 to the x. It's one way of looking at it. So how does this work? Well, when x is 0, this is 2 to the 0 power is still 1, it's 1 over 1, we still cross here. So this function, this purple function, is going to cross in exactly the same spot, 0, 1. On the other hand, when x equals 1, this is 1 over 2 then, or 1/2. So this is here. And as we get bigger and bigger and bigger numbers here, 10, 100, 1,000, the denominator is going to get larger and larger and larger, and this is going to exponentially decay down towards the x-axis of 0. It'll never hit 0 because we'll never be able to get small enough to get 0. We'll always be some little fraction away from 0. All right? And then when this is 1, or when this is minus 1, that flops this 2 back around to the numerator, so it's then 2. So this equals 2 here. So this is minus 1, 2. And this looks like a mirror image of the red line. So it's symmetric, we say, about the y-axis. And it looks something like this. Well, in science, we're usually interested in starting at 0. Like, for example, say x represents time. We don't start at negative time. We usually start at time equals 0. And we go forward. And if we follow this red type of function, we call this exponential growth. Just going to put exp growth. And if we follow this purple function from 0, we call this exponential decay. Lots of things take on exponential growth, like for example humans or biological organisms. We usually grow exponentially unless there's something to impede that process. And some things decay exponentially. For example, radioactive material will decay exponentially. So these are just a couple ideas represented here. So let's plot a special function, a special exponential function that looks something like this. Here, f of x equals something we call e to the x, where e represents the number 2.718. 28 ... goes on forever. So e is a special number. This is raised to the power of x. So this is a neat function, but it behaves the same way as the other exponential functions. It still crosses at 0, 1, but now here at 1, the value of a is e. And again, this goes off towards 0 on this side. And it comes up and it grows at a pretty rapid rate. Now, the exponential function is a really cool function. So we call this the exponential function, because if you were to take the slope of the exponential function at any point, it doesn't matter what it is, the value of the exponential function equals the slope of the exponential function. So the value of the exponential function at a point equals the slope of the exponential function. So for example, the slope of the exponential function here, where we cross the y-axis, is going to be equal to 1. And the slope here, where we cross, where we intersect with the exponent and 1 in the exponent, is going to be e. And there's no other function that does that. That's pretty cool. Most other functions, they might have one spot where the value of the function equals the slope of the function, but not the exponential function.